two parts because I smushed two things together. Because I figured some people would be interested in one thing and some would be interested in the other, but hopefully together they'll be an interesting talk. As Greg said, the first part is on how to achieve low latency in shared environments, especially where you're running lots of different kinds of processes on lots of machines, and you want low latency response time for interactive kind of services. And the second part is on how do you learn high-level representations in a bunch of different domains via deep learning for neural nets. Okay, the first part. So why do we care about low latency? Well, if you can build applications that feel very interactive, then users are generally happier. They can understand, what the results are going to look like sooner. So if you can actually, for example, update the results page as users are typing, that's a pretty interactive feel. And that actually requires a fair amount of computation underneath the covers in order to sort of accomplish that. So just to give you a sense, a query comes into one of our data centers, and in order to assemble the data on the results page, there's a huge amount of subsystems that need to be involved. Our ad system is one thing that actually has 150 subsystems itself that I just folded into one little box. The search system itself has lots of different kinds of subsystems for searching different kinds of information, combining these things. Once you get results, you need to decide, is news relevant for this particular query? Or are book results relevant? So there's a very large fan out in order to accomplish all this, to search over all the data that we want to search over in order to give you results and to kind of put it all together and format it in HTML and so on. So one thing that helps with interactivity is being close to the user. So that's why we have data centers in so many places, is because the speed of light matters to get to, from the user's machine to our data center. And so if we only had one data center in the world, then there'd be a significant penalty for people on the other side of the world. So we have data centers scattered around the world. And let's just zoom in on one of them. We have a professional photographer who takes nice data center pictures. So. This is our data center in Oklahoma, actually. And you can see these are pretty large facilities. They kind of stretch on for football field kind of lengths. There's lots of different machines in them, but they're all pretty much the same design. We've gone back and forth whether they should have some sort of cases on the front or not over the years. But essentially that's what you have. You can save some power, although most of the power in the data center is not from the lights. Even the cooling facilities look kind of neat. Anyway, so on each of those machines in this data center, our environment is shared. So all the different services that we operate, including batch computations, interactive computations, are all running on pretty much the same basic machine structure. So we have Linux underneath all of this. We have, for example, daemons for our distributed file system running on every machine pretty much, a daemon for our scheduling system, some other system services. And then on top of that, we have a whole bunch of kind of random application and sort of higher level system services. So a Bigtable is like higher level structured storage system we've built. A lot of machines run a process involved in that. We might have some random CPU intensive job, some random MapReduce job that someone's running to compute something, some other random things. And that's sort of the picture of a typical machine at Google. There's all kinds of stuff running on it. Some of them are interactive jobs. Some of them are kind of batch jobs where you don't necessarily care about interactive latency. And the reason you do that is because you get greatly increased utilization. If you dedicated machines to each one of those tasks, most of them wouldn't necessarily fill up a machine's capacity. And so by multiplexing effectively the computational resources on these machines across lots of different jobs and tasks, you get much better utilization of your expensive computing hardware. But the problem with that's the plus side. The downside is that you get these really hard to predict effects that increase variability. And the variability increase is really a problem for interactive jobs. So for example, some of the things that can increase variability are network congestion, background activities running on the machine, bursts of foreground activity, so some other job kicks up and all of a sudden starts to use 80 CPUs on the machine for a little while. And the bigger problem is that it's not just your jobs. So if you were designing a system and you were running a bunch of things on these machines, that would sort of be okay because you'd kind of understand at least what's running on the machine. But because we pack all kinds of things on these machines, that you now have to deal with sort of an exponential number of possibilities of things running on these machines. And everyone else's jobs get in your way too. And it's not static because these jobs come and go over time, over periods of 5 minutes, 10 minutes. The shift of tasks on the machine might change a bit. So this kind of change in the load on the machine is changing constantly. And it's made worse by large fan-out systems. So the search picture I showed you where we need to fan out a request to thousands of machines, do some local work on each one of them, and then get the results back, is a real serious problem for variability because you need to wait for all or 99.9% of the results to come back before you can really decide what are the top results going to be. Can I format them? Can I generate the titles and snippets that I'm going to show on the results page before doing that? So, to make this clear, the problem with shared environments is when you look at your own code, it always looks really, really fast. Unfortunately, if you look closely, I don't often get to use my vacation pictures, so they have a really long tail.
Just a quick question. When you mentioned about the shared environment, are these virtualized or non-virtualized?
So the question is, are these virtualized or non-virtualized? We don't run VMs, but we effectively have our own system that runs separate processes that are sort of kind of like what you would do if you were running VMs. They're just running different Linux processes on the machine. Okay, so to make this concrete, if you have a server who has an average response time of 10 milliseconds, but 1% of the time it takes a second to respond, then if you need to touch one of these in a fan-out request, that's not really a fan-out, I guess, then 1% of your requests are going to take more than a second. If you need to touch 100 of these and get results back, and you need to wait for all of them, then 63% of your requests are going to take more than a second. That's the problem with variability and fan-out. So, what can you do? Well, there's a bunch of different things that are sort of just good practice to do in order to reduce variability. The first is if you have different kinds of service classes, like you have some interactive requests and you have some non-interactive requests, you should prioritize the interactive ones above the non-interactive ones. Sort of common sense. You should probably do this at your network level within the data center, so you want to prioritize interactive traffic higher than some random read of data for a batch job. Sometimes you want to reduce head-of-line blocking, where if you have a really large request, you kind of break that into a bunch of pieces and do a little bit of work on each piece, and so that you allow smaller requests to kind of jump in the middle and get better interactive response for most of the requests at the cost of that one large request. And you need to manage the kind of expensive background activities that a lot of different systems often have. In a distributed storage system, sometimes you do log compaction periodically, which is a kind of big bursty activity. And maybe you can defer that until you know the load is low on the machine, or when you know the load is lower at night, these kinds of things. Okay, so these are just kind of like good hygienic things to do. But the real issue is you really need to be tolerant of variability in your system. And I'm going to make an analogy to fault tolerance, where essentially you're going to take extra resources to make a fault-tolerant system, and you're going to make a reliable whole out of a bunch of unreliable pieces. So if you have a bunch of disks, you can make a rated file system that is much more reliable than any of the individual components. So in order to tolerate variability, you're going to do the same kind of thing. You're going to use the same extra resources you already need in place in order to tolerate faults. And you're going to make a predictable whole out of unpredictable parts, a more predictable whole. So where the analogy kind of breaks down is that the timescales are quite different. So for tolerating faults, where you actually have hardware failures you need to deal with, there are not very many of those per day. it's kind of tens of failures per day. The scale of recognizing those and responding to those is kind of tens of seconds, maybe a minute kind of thing. Whereas for dealing with variability, you're going to get thousands of disruptions per second in a large cluster running lots of jobs. And you need to deal with them on the scale of milliseconds, because you want to deal with them while the user is actually waiting for their response for some higher level request. So there's a couple of different classes of latency toleration techniques that we've kind of come up with over the years. I'm going to mostly focus on one of them in this talk, but there's a bunch of them. We had a CACM article in February this year where we outline a few other ones. But essentially they fall into two classes. The first is what I'll call cross-request adaptation. So you're going to examine recent behavior in your system, measuring load and CPU utilization, maybe number of disk requests, those kinds of things. And you're going to take action to improve the latency of future requests on a time scale of tens of seconds or minutes. So it's not going to help a user who's got a request for a search now, but it might help users in a minute or so who send you requests if you can essentially better balance the load across your whole distributed system. And then there's what I'm going to call within request adaptation, where essentially you're going to want to cope with something that's being slow right now while the user's waiting in order to essentially get their results faster. And I think that one's kind of more exciting because you need to respond really quickly and figure out what to do. So I'm going to describe one technique that we've come up with that's actually pretty effective. And it has the exciting name, backup request with cross-server cancellation. We struggled for a better name, but what can you do? So the idea is, suppose you have a few alternative replicas that you could send a request to. Maybe in a distributed file system, every chunk of data has been replicated on 3 different machines. And so any one of the 3 machines could service your request. So the idea is you're going to, normally you pick one, send the request there, and wait for it to come back. And you might have some really long timeout in case the machine died. And after 10 seconds, you'll send it off somewhere else. But instead, what you can do is, here's my client request. I'm going to send it to one place. And then very soon after, before I really expect a response, I'm going to send it to the second place. Send it to the second server. And the identity of that request is also the identity of the other servers included in each request, so that I know each server knows which other servers might have received a copy of the request. And then they're going to continue processing requests. And then server 2 is going to start processing this request first. And just as he starts to do that, he's going to send a message to server 1. He's going to say, by the way, I'm starting on request 9. You might want to know about that. And then server 1 can decide what he wants to do about that. He could, for example, drop the request entirely from his queue because he's like, oh, great, server 2 has it. I don't have to deal with it. That would be a fine policy. He could deprioritize it but not completely drop it. And so if he has extra resources or idle time on his disk, he could issue the read. And then server 2 is going to process the request and send the reply back to the client. Simple enough, right? Not so hard. It's a couple of UDP packets flying back and forth just to tell the other guy what's going on. Okay, now obviously there's a bad case here where we do this, we do that, and they both kind of at roughly the same time decide, oh, I'm going to start the request. So there you go. There's our UDP packets flying back and forth. And they're actually going to do the read. Now, you can actually check again when you do the read and have a tie-breaking policy about who's actually going to respond. So you've now done 2 disk reads instead of 1, but you don't necessarily have to incur the network traffic to send 2 replies. So that saves you a little bit. But the good news is, the faster your network is, the closer together server 1 and server 2 are, the less likely this window vulnerability will happen. Because it's only sort of if they both decide in one network hop worth of time that they're going to do this, that you end up doing 2 disk reads instead of 1. Yeah?
On the other hand, having them closer together means that the odds of them both spontaneously dying at the exact same instant is distinctly higher.
Well, they don't have to be like right next to each other. Like I'm talking in the same building, not like one in Amsterdam and one in Ireland or something.
If the entire building burns down, it's still a problem.
Fair enough, but you can handle that at a higher level. It's definitely not good to handle the building burning down within the building. Okay, and then you get to reply. So, as I said, the likelihood of this bad case is reduced if your network is lower latency. And that's kind of good news because networks are generally trending downward in latency. Okay, so let's see how well this works. So we modified our system. Actually, this is a monitoring request through a big table cell. And then the big table cell itself issues reads to distributed file system files. And so we modified our distributed file system, so if it has 3 replicas, it sends a request to one of the replicas. It waits 2 milliseconds, which is generally faster than you'd expect to get the response back from the first replica, sends to the second replica, and then the servers do this cross-cancellation UDP packet. And we're going to measure the time of how long it takes to do a high-level monitoring app that might involve one or a few disk reads in total. So if we look at the cluster state, if the cluster is mostly idle, so essentially the only thing running on it is this big table cell and not much else. This is the shared environment in the good case where there's actually not that much sharing. Then you see the latency profile of these high-level monitoring apps, where, for example, the 99th percentile is 67 milliseconds. But if you do backup requests, then that drops pretty substantially, 43% reduction in latency, and pretty good reduction in other points in the latency distribution curve. So that's good. But what about if you're also running a really intensive sorting job on the cluster? So this is essentially running a big MapReduce that's sorting a huge amount of data. And so now all the machines in the cluster are essentially doing a lot of other work in addition to trying to service your monitoring apps. And you see the latency goes up a fair amount in both the no backup and the backup case. That's sort of what you'd expect because now there's other stuff going on. But you still get this very nice reduction in tail latency, which is pretty nice. And you only do about 1% extra disk reads. So that's pretty good. Like, I'd be pretty happy with it. I am pretty happy with that trade-off. So there's another interesting way to look at this, which is if you look at the mostly idle state with no backups, that latency distribution looks an awful like a cluster where you're running a ginormous sort job and you're doing this backup policy. So that's pretty good, because that means you essentially get a really big batch cluster for free on your interactive cluster, right? Basically, you have the same read latencies for your interactive job as no backups for the completely idle cluster.
Do both of those processes have the same next level?
Yes. The question was, do all the processes have the same nice level? Yes. Okay. So that's kind of the nice latency story. You should try, and you can do this not just for disk requests, but for other kinds of requests in interactive distributed systems. Yeah.
So what happens if you do cross-server cancellation and then the one who is actually serving dies?
So the question is, if you're doing this cross-server cancellation and one of the servers dies.
The one who declared that it is not doing the job.
Right. So you have the same problem. So you have the same problem as if you sent the request to just one server and that server died. You need to have some policy for that, and probably, you know, your TCP connection maybe drops, and maybe you recognize that, and then you send it, or you have some long timeout of 10 seconds or something, and then you send it to someone else. And in fact, this will actually help you because if you didn't delete the request in the other server but just deprioritized it, you would eventually get a response from him probably faster than you could recognize that. Okay? All right. So now we're going to switch gears. All right. So one of the things we've found over the years is that if we can build computing systems that give you a nice high level of abstraction that just works, that makes people much more productive. They're able to kind of use these high level of abstractions to do interesting things on top of them without necessarily worrying about what's going on under the covers. So MapReduce is a good example of this. You can write nice MapReduce computations and not worry about the fact that machines can fail underneath you, because that abstraction layer takes care of it for you. So more recently, I've been looking at, with a bunch of other people, how can we build high-level systems that are able to build nice high level of abstraction in domains like machine learning. So there's a lot of machine learning work at Google because a lot of the problems we're trying to solve are fairly complicated, and we have a fair amount of data, and in order to accomplish them, you can often use that data to build statistical models of the problem you're trying to solve.
Is there some distinction between a high-level system that just works and an application?
Yeah, so for example, a high-level system that just works might be something like MapReduce, where you're building other software on top of that.
So you're talking about things with exposed APIs to other things?
Sure, yeah.
Okay, yeah, I was wondering what the scope was.
The scope is that if you're able to build these levels of abstraction that hide a lot of complexity through nice, well-defined interfaces, then that frees up a lot of innovation to happen on both sides of the abstraction boundary. You can sort of replace the implementation underneath the covers and do a lot of interesting things underneath the covers to make the implementation of that interface better. And on top of that interface, people can treat the specification of that interface and build upon that without having to worry about what's going on underneath. Does that make sense? Okay, so the idea of this work is, can we build systems that are able to essentially generate a high level of understanding from raw data? And we want to actually solve difficult problems. Obviously, we want to improve Google's products. And we want to minimize the software engineering effort, where a lot of machine learning algorithms, you need to essentially hand engineer features you think are predictive of some high-level task that you're interested in. We'd like to sort of get away from that, because that's a fair amount of effort in doing so. And we want to sort of learn from raw data and build these high-level abstractions automatically. So there's no shortage of data. There's an awful lot of kind of different domains of data in the world. There's lots and lots of text out there. There's plenty of visual data, both static images and videos. There's lots of audio data, and user activity data is another interesting domain. And we have a thing at Google called the knowledge graph, which is essentially a hand-curated set of triples, relational triples, where you can say Albert Einstein, born in Switzerland, and billions of these kinds of labeled triples. So that's kind of the raw data that you can imagine applying to these sorts of problems. And then we want to be able to do things like, for example, identify what are the main objects in a static image, and and also where in the image are they located. So this is a pretty hard problem. If you look at the bottom row, those are all tractors, but they're all from different viewpoints. There's different colors involved. They're different kind of scales of tractor. The background's kind of different. This is a pretty difficult task. If you look in the upper right, you might say car, but it'd be better to say car show, because there's a guy in a suit on a turntable. And that actually is a better label for that particular image. Car would be a fine additional label to give. Okay, so that's one thing we want to be able to do. We have a bunch of kind of finer-grained tasks that we want to be able to do. For example, in our Street View project, we have imagery collected from taking pictures of street scenes, and we want to be able to read house addresses out of this imagery. And that comes in a pretty wide variety of fonts and orientations and so on. So you need to be able to first identify something that might be a house number, and then ideally read the numbers out of it, despite this sort of wide variety of fonts. And then more generally, you might want to be able to OCR the world. So you'd like to be able to read all the text in that scene and associate it with the location and the business, and know what businesses are present in this location. You know, if you can see well enough, there's actually hours posted in some kinds of scenes like this. You might want to know the opening hours of businesses. If you can read the window, that would be cool, right? We don't actually have much of that kind of data, but you might want to be able to read that. We have more of that kind of data. We want to be able to read that. And really, there's an awful lot of visual data, and we have a whole bunch of different kinds of tasks we'd like to be able to do. And there's some common visual representation that's going to be useful for providing higher level features than just raw pixels to all of these different tasks. And so we'd like to be able to build a system that can accomplish all those different visual tasks I described, plus a bunch of other ones, and also do unsupervised training where you don't have a particular task in mind. You just want to be able to learn to have a good model of what kinds of things you tend to see in images. Similarly, we'd like to be able to know what is being said in this audio waveform. So time goes that way and different frequency domains go vertically. That actually is a pretty important problem. You want to understand what people are saying so that you can do voice queries, do dictation, these kinds of things. And understanding the lowest level of waveform is kind of the first part of speech recognition. And similarly, across all these different domains, there's a bunch of tasks in each domain, but you'd like to be able to sort of build these common representations across different domains. So if I'm given an image, it'd be nice to be able to emit a textual label for it. And if I'm given a textual label, I'd like to be able to generate images if that's a visual kind of text label. Like if I say cheetah, if I type in cheetah, it'd be nice to be able to sort of find representative cheetahs. I'd like to be able to say the word cheetah, all these kinds of things, right? Okay, so we've been using neural networks for the last couple of years to work on a bunch of these different kinds of problems. So neural nets essentially learn a complicated function from data. So you have some space 1, which might be input pixels. And you have some space 2, which might be labels of what you think is in that image. And you're going to learn some very complicated function to map from the pixels of the image to what you think is in the image, for example. They're made up of neurons. So you have a bunch of inputs to a neuron. This is kind of an abstract model of how human or animal neurons work. You have some inputs. They each have some weights. You do a weighted sum of those inputs, and then you put the result of the weighted sum through some nonlinearity. Traditionally, that's been a fairly mathematically smooth function like a sigmoid, but more recently people have been getting very good results with that nonlinearity, which is just the max of 0 on the value. So that's a single neuron. A neural net is just a bunch of connections of these things. So you have some inputs, and you have some outputs, and data just flows along these edges, which are all have weights associated with them, and there's your output. So learning in a neural net is fairly simple while you're not done, like while you're not happy with the results. You pick a random training case, which gives you both the input and the desired output for that training case. You run the neural network on the input, see what it says, and then you modify the connections to make the prediction closer to the desired output if you didn't get that desired output. And most training involves something called gradient descent, where essentially you're trying to essentially get to that minimum value of that function, and you're at this point on the side where the little ball is, and the gradient kind of tells you which direction you should go. Now this is a very simple two-dimensional picture, but actually in a neural net with a lot of parameters, you're trying to optimize this sort of 10 million dimensional or 100 million dimensional function. And so it's got lots and lots of very complicated sort of peaks and valleys in it. And you're trying to find the global minimum, but you're not probably going to do that. You're going to settle in some local minimum in this very complex function landscape. So the deeper your network is, the more nonlinearities it goes through, and the more sort of complex functions you can learn. So we can actually train 10-layer networks. We sort of can do it. There's not a lot of theory in terms of mathematical theory about non-convex functions and how they behave in this complex domain. So some of the things that even a small network with 2 hidden layers can do, which may be kind of surprising to you, you can actually sort a bunch of numbers, you can multiply numbers, you can compute analytic functions. These aren't necessarily obvious. In the actual neural network domain, what can a 10-layer network do? So in 1/10 of a second, humans can recognize objects. They can recognize speech. They can see if you're smiling or not. Instantly look at some task that you're trying to do, like take the lid off a bottle, and instantly know how to do that. And the firing rates of neurons are such that you couldn't have gone through any more than 10 sequential levels of neural activity. So just to make that concrete, a human sees an image of a cat. In 1/10 of a second, they're able to click with the cat. So that's pretty cool, right? Humans are putting a huge amount of computational effort to this, but it's only going through at most 10 layers because the firing times dictate that you couldn't have gone through more.
Is that after they've already optimized for that specific interaction, or is that just out of the blue?
Out of the blue, you can mostly do it. Yeah, it might be 1/15 of a second or something, or sorry, 0.15 seconds or something instead. So there's a conjecture that anything a human can do in 0.1 seconds, the right 10-layer network should be able to do. The trick is finding the right 10-layer network and making it big enough. But the good news is big is not exponentially big, right? There's examples of small organisms that do have perception, like the lizards that can see. And it doesn't have to be any bigger than that in theory. One thing we've observed is that the number of training cases needs to be roughly about the number of trainable connections in your network. And so that whole approach is pretty feasible if you're motivated and excited about it. So how do you solve it? Well, first you need a fast network implementation, neural network implementation. The reason you want that is so that you can train bigger nets in the same amount of time. Our observation is that, at least with our group, people have a limited patience for training a network. They don't want to wait a year. They want to wait kind of no more than a few days or maybe a week. And so you're going to train the biggest network you possibly can such that it only takes you a week. And so if you're able to train a network faster and train a bigger network in a week, that's good, because that means that people will be more willing to train a bigger network because that matches their 1-week threshold. Okay, so human perception is clearly fast. It can't go through any more than 10 layers in 1/10 of a second. And thus, you can solve a lot of perceptual tasks using some 10-layer network. So the question is, why do we need so much training data? And the answer is, I actually don't think it's that much more training data than a human needs. It's a bit more, but if you think about all the training your visual system has done from the time you opened your eyes when you were first born until the time someone put that first picture of a wallaby in front of you, something you've never seen before, there's a tremendous amount of information you've collected, and you've built these models of what does an animal look like, or what does a furry animal look like. And so when you see a wallaby, you're training on that plus all the accumulated knowledge you've put into your visual system before that. So I'm going to talk about 2 main tasks, speech recognition and visual object recognition, that we've been exploring. And neural nets these days give the best results in these 2 domains. So how is it done? Well, you need a big training set, labeled data, so a bunch of images, for example, and labels that say wildebeest, truck, garbage truck. And then you train a big network. There you go. So neural nets have been around for ages. What's different? So the main things that are different are we have a lot bigger data sets with labels. and also without labels. And we have much faster computers. So slow machines are really an impediment if you're trying to do this, because these big networks require millions of floating point operations per example in order to do the forward propagation pass, and then millions more flops in order to do the training adjustment pass. So you really need a lot of computational resources in order to do this. The question is, how are we able to go to much larger numbers of layers today, whereas maybe 15 years ago we could only go to a few layers? The answer is you need many more training examples in order to optimize a very deep network, because the function you're trying to optimize is very complex. And so more training examples give you a better sense of gradients and where you should end up in this very complicated space. If you don't have enough training data, then it's very difficult to train.
Been supervised, all 10 layers?
Yes.
Supervision?
Okay. So I think this kind of gets to your question, which is that in the past, people have kind of limited the number of layers they trained because, the data sets were small, computation was expensive, and it turns out that deep networks actually build these very high levels of abstractions much better than sort of a shallower network. And so this is why this field is now called deep learning. You can think of deep learning as just very deep neural nets and other kinds of models that are able to build these high-level abstractions. You can actually learn from both labeled data and unlabeled data. And there's been a bunch of recent academic work that improves on state-of-the-art in many different domains. Most of it by Jeffrey Hinton, Andrew Ng, Sammy Bengio, or Yoshua Bengio, and Jan McCoon, and a bunch of other people. And those domains where this kind of approach is being applied started out kind of a few years ago where they were getting state-of-the-art results in images and speech, and they're now moving to video and natural language processing and other kinds of tasks, using fairly modest model sizes. So the approach we're taking is we want to build much bigger models and be able to train those much bigger models on big data sets. And so the general approach that we've taken is we want to parallelize this computation at lots of different levels in order to do this. So to make this concrete, for an image model, we essentially have neurons at a bunch of different levels that each look at a fairly small local set of inputs. So they don't look at the whole layer below them, they look at a smallish patch. And we essentially take one of those models and partition it across a bunch of machines. And so that gives you additional computational resources to devote to training these networks. Because the connections are local, that has the nice property that, for the most part, no data needs to be transmitted across machine boundaries. Only kind of that second neuron's data needs to be transmitted across machine boundaries because it falls on both sides of the partition boundary, the input for that neuron. So for example, one of our biggest models is 144 machines, and we're using 2,300 cores to train it. The basic idea behind training is we're going to use either an unsupervised or supervised objective, and we're going to do what's called mini-batch stochastic gradient descent. So we're going to take in, order 100 images, run them through the network, compute a gradient that makes the output of the network better for those 100 examples, and then we're going to push gradients down and adjust the parameters in the model. Now actually, that's still not fast enough for our 1 week tolerance. And so we actually add another level of parallelism for training these models. So each one of those boxes at the bottom is one copy of a model spread across a bunch of machines, each of which has a bunch of cores. And now we're going to use data parallelism. So they're each going to train on different examples at the same time. And before they train on a batch of examples, they're going to get the current state of the parameters for the model, the weights on the edges. And they're going to run the examples through, they're going to compute some gradient, and send the adjustment that they'd like to make to the parameters up to this centralized parameter service. And that itself is spread over a bunch of machines. And so then the parameter server is going to be the one that actually applies the gradient. So it's going to compute new parameter values by taking the old parameter values and then adding in the gradient that it was just set. And then the next step, it's going to get a new copy of the parameter values, compute a new gradient, and do the same thing. And what actually happens is we're going to be doing this asynchronously in parallel across lots and lots of replicas of the model, each training on different examples.
So you're not getting these deltas in lockstep.
That's correct. So this is all asynchronous. And as you point out, the main drawback is that when you downloaded the parameters, you computed a gradient with respect to that value of the parameters. And in the meantime, while you were running your step through, some of the other models may have sent gradients to the parameter values and updated them so that when you're applying the gradient, you're actually applying it to a moved version of the parameters, not the ones you originally computed it on. But it all seems to kind of work. So, what can you do? Up to maybe 10 to 100 replicas of the model, depending on how sparse the gradients are in the model. Okay.
How big is the typical vector of, P?
So the vectors, most of our model parameters are, 100 million parameters. So 100 million floating point values. Some of them are a billion. But that's why you have a lot of network interfaces at the top and a lot of network interfaces at the bottom. The question is how many attributes are in the input. So the input, for example, might be all the pixel values in an image. So, a 200 by 200 image with 3 channels. Actually, our biggest models are for video, and there you kind of take that in, but for maybe 10 or 15 frames. Okay, there's lots of interesting trade-offs that I'm not going to go into much. You can use lower precision arithmetic. It turns out these things are pretty tolerant of noise. So, 16-bit floats are fine. So the question is, what are the precision levels in human neurons like? And I don't know, but I suspect it's not more than about 4 or 5 bits. That'll be my bet. So, yeah, 16-bit even seems like overkill. Okay. So that's kind of the basis of the training system that we've been working on. Let me talk about some applications. So when we first started this project, we initially focused on doing unsupervised learning, where essentially you have a very large data set, but you don't have labels of what you'd like the output for different input examples to be. You just have, say, a bunch of images. And in particular, an experiment we did was we took 10 million YouTube videos, we took 1 frame from each of them. And then we trained in an unsupervised manner, so we didn't know what was in the images. The model never was told what was in the images. It just got 10 million YouTube frames. And we told it to try to reconstruct the input from the representations it had learned in these different layers. So essentially, if you think of it as how a human would do it, if I can build a high-level representation of this room, I would say it's got a bunch of people in chairs in it, and it's got an easel, and it's got some walls. And you could reconstruct a rough picture of what the room looks like from that.
Was the net hourglass shape, so you were doing compression and then expansion?
Yes. Okay, so then once we've trained the network on 10 million completely unlabeled examples, we looked around at the highest layer using a data set that we knew to contain half faces and half not. And we looked around for neurons that were receptive, most predictive of whether or not an image contained a face or not. And the one that we found, that is the optimal stimulus for that neuron. So essentially, the network, without ever being told what a face was, has developed a neuron that has invented the concept of a face, essentially, which is pretty cool. Since it's a YouTube data set, we have another neuron that has invented the concept of a cat.
Did you answer the AI question on what is a chair?
Yeah, I don't know. We answered what is a cat, which is good. Maybe a more important AI question. So the question is, how does the training time vary if we increase or decrease the number of layers? It's hard to say, but generally more layers and more parameters takes longer to train, and it's probably slightly superlinear. The question is, how do we decide the number of hidden units per layer and essentially the model structure that we trained? And that's kind of an unsatisfying thing to me. Right now, we kind of decide that as humans training the model beforehand. And you try a few things, and that one seems to work better, so you do that. Which is kind of unsatisfying. We should really be learning the model structure as well. We're not doing that. Okay, there's a paper in ICML. If you'd like to see this. Our colleagues kindly gave us a nice commentary on social work. Okay. So the second thing we were working on was a collaboration with the speech team, where essentially we wanted to do a deep neural acoustic model. So we essentially want to take in some small snippet of audio. That bottom image of audio is about 250 milliseconds of audio, and at each 10 millisecond interval you get 40 floating point values that describe the frequency distribution of the audio signal. And the goal of the network is to predict what is the phoneme being uttered in that middle 10 milliseconds of speech. So you get some context, and you need to say, is that sound a b or a ps? Something like that. And then there's a language model on top of that that tries to string a whole bunch of these 10 millisecond predictions of phonemes into a sequence of words and sentences and phrases. This is just kind of the first half of that pipeline where you're trying to go from raw signal to predicted phonemes. And so that's essentially what we did. It's actually a pretty simple architecture. It's just a bunch of fully connected layers, and then a softmax layer at the top that tries to predict the phoneme label. And we have a bunch of labeled data for this. And essentially when we first deployed the neural acoustic model instead of the previous model, which was based on Gaussian mixtures, we got a 30% reduction in word error rate for English. And one of the people on the speech team said, wow, that's the single biggest improvement I've seen in my 20 years in speech. I'm not a speech person.
How many layers?
When we first deployed it, it was 6, and it's a little more now. And this has been launched since Jelly Bean. So when you're speaking into your Android phone, that's what you're talking to. So remember how I said we wanted to be able to combine lots of representations together for different tasks? Well, one example of a different task is I might want to be able to recognize Portuguese instead of English. And the problem with Portuguese is we don't have very much labeled data for Portuguese, especially compared to English. So the word error rate for Portuguese is a lot higher because we just don't have as much labeled data, so the network doesn't perform as well. So one thing you could do is you could just, well, say English and Portuguese, it's kind of the same. Let's just, instead of randomly initializing when you start training, let's just start with the English weights. And that actually works. You get a little bit of reduction in your word error rate for Portuguese. Great. But another thing you could do is you could say, well, English, Portuguese, Spanish, they're all really kind of the same. Especially at the low levels, that makes sense because they're all kind of dictated by the human vocal tract. And a lot of the features at the low levels should be the same, essentially, across all these different languages. And so, essentially, you can train all of these things jointly, where you take in all your English data and you train an English model that shares, say, the first 6 or 7 layers, and then has a final layer or 2 that's English-specific, and then do the same thing for the other languages. And that actually reduces your Portuguese error rate even more. Because now you're not just using English data, not just initializing from English data, but you're also taking advantage of the Spanish data and the German data. Maybe the German data is not that helpful, I don't know. Maybe not for Portuguese. And so you get a pretty nice improvement. It's not bad. And the interesting thing is your English performance actually gets a tiny bit better. So that's cool too. Not bad. So that's an example where you have a whole bunch of tasks. You've built a common representation, which you can think of as the top layer that's shared here. And that's useful for other tasks you may not have thought of. If you want to add a new language to this system, you can start with this representation and probably be much better off than starting from scratch. Yeah?
Does it make sense to have more than one layer at the top?
Yeah, does it make sense to have more than one layer at the top? Yeah, probably. You know, we've done a few experiments. 1 seemed pretty good. 2 is a little bit better, but maybe not worth the hassle. Okay, so now I'm going to talk about a convolutional model for object recognition that was originally developed by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton when they were at University of Toronto. They're now at Google. So it looks kind of similar to the model that I showed you before, except now we're going to do supervised training only. So we have enough images with labels where it says, you know, a picture of a wildebeest, and we have a label that says wildebeest. We have, you know, order a few million of those images with labels. And we're going to use a convolutional network, which was originally developed by Jan LeCun. And the idea here is, in the first experiment I showed you with the unsupervised training, the weights on the neurons were completely independent at different locations. So in a convolutional model, that's not the case. You're going to keep the same weights within a layer and just apply those weights at all the different locations in that layer. This has the advantage that you now have many fewer parameters in the model, but you still use a fair amount of computation. You can make a big model with fewer weights by using a convolutional structure. And then at the top, you get a bunch of outputs that are kind of still spatially oriented a bit. And then we're going to use some fully connected layers at the top, and then softmax to predict which of 1,000 different object classes something is. And this is actually released initially as part of Google Plus photo search. So you can actually search photos that you or people have shared with, that you've posted or people have shared with you. And you can type in queries like statue, and it finds things like that, even though they haven't been labeled. So that's just from the raw pixels of those images. And this is what one user thought. They're like, wow, the new Google Plus photo search is a bit insane. I didn't tag those. That's cool. And you can find sea, drawing. And if you're going to have only 1,000 classes, or 2,000 classes, you should have a macrame Yoda. Well, a Yoda class that can find a macrame Yoda. So that's cool. And that's actually pretty useful, right? Being able to understand what is in images is clearly something pretty useful that computers have traditionally been pretty bad at, and this is kind of pushing them towards not so bad. You can also use this for more specialized tasks. So my summer intern this summer trained a model to detect where text was in a street scene. Remember I said we wanted to be able to read the text in kind of arbitrary street scenes. Well, the first thing you need to do is find the text. You know, so this is actually a pretty difficult problem, finding text in arbitrary scenes. There's all kinds of fonts involved, different colors, and this model does a pretty good job of highlighting that.
How long does it take?
So the question is, how long does it take for training or for actually finding the text?
Finding the text.
Well, you can always parallelize it more. So, you know, it might take, you know, half a second for an image or two. So the question is, does it work equally well on scaled images? Yes, so it does. Because the imagery that we trained on actually has text at a whole bunch of different scales, because as the car drove by, some things are really close, and so it has like open, and some things are really far away, so it has a little open. And as long as your training data represents all the different kind of rough scales of text that you're going to want to recognize, it'll do a pretty good job. So there was actually some of my colleagues competed in being able to read text out of arbitrary street scenes, and that's their entry from Google. And it's quite a bit better than the other entries in this particular contest. So it's getting pretty close. 82% correct words is, not so great, but it's good enough to kind of start thinking about indexing things. And if you have lots of different views of the same business, then probably you'll end up getting it right from one of the 4 or 5 views that you might have. Okay, so those were kind of perceptual things: speech, vision. How can you use these for text? So one of the techniques, neural nets are good at dealing with kind of dense numeric representations. And it's not obvious if you have the word porpoise or dolphin how you turn that into something that a neural net wants to consume. And the main trick that you can use is you can say, I'm going to represent each word by a high-dimensional vector. And so let's say I'm going to take the word porpoise and pick a point in a 1,000-dimensional space, maybe in the 1,000-dimensional unit sphere. And I'm going to do the same thing for the word dolphin. And the hope is that if I'm able to do a good job of training a model that uses these embeddings, that words that are very closely related are going to end up being very close together in this high-dimensional space. So we want porpoise and dolphin to be close together. I like to say they have the same sense of porpoise. And then we want a word like SeaWorld to be kind of nearby, not as close as porpoise and dolphin, but kind of nearby, and a word like Obama or Paris to be pretty far apart from porpoise and dolphin. And so there's a bunch of different models you can use to train these embeddings, but essentially you take a word in, you put it through the embedding to figure out what the current 1,000-dimensional representation of the word 8 is, and then you're going to use it to use that vector to try to predict some of the other words that are nearby. So if I see the word 8, I want to be able to predict the word cheese. And so the hope would be that I'm able to do that. And if I am, great. If not, then I'm going to make little adjustments to the embedding vectors to move 8 around and move cheese around so that I'm better able to make that prediction. Same way you would do stochastic gradient descent. You're just doing that here, and you're pushing not only the neural net layers, but also the embedding vectors around. And so here's some examples of some embedding spaces that have been trained. And if you take a word like apple and you look at what are the nearest neighbors in this embedding space, and what you see are fairly semantically related words. You see fruit, you see apples, you see melon, peach, other kinds of fruits.
No Samsung.
Yeah, so this lexicon was actually case sensitive. That's why you don't get apple the company, you get apple the fruit. And it works for verbs. So, stab is kind of like punch, which is kind of like shot, and thrust. And it works for proper nouns like iPhone. iPhone is kind of like iPad and iOS and smartphone and iPod, like iPhone. So it turns out these embedding vectors trained to do language modeling, where you're trying to predict a nearby word, actually have pretty interesting properties. So it turns out linear arithmetic on these embedding vectors actually makes sense. So if you want to solve analogies, if you think back to your SAT days, hot is to hotter as big is to what? Well, if you have those 3 embedding vectors and you do the arithmetic on them, just linearly adding and subtracting vectors, the nearest embedding vector to the result on the left-hand side is the word bigger. And it works for country capitals. It actually works surprisingly often.
Antonyms?
Yes, so you can do antonyms as well. You could do hot is to cold as large is to small. So in order to show you why this works, we can take the high-dimensional vectors for countries and capitals and project them down to 2 dimensions so we can actually see them on the screen. And we're going to project them down with principal components analysis for a bunch of countries and a bunch of capitals. And you see why this works, because you go in roughly the same direction from the country to get to the capital for each of these pairs, right? So that makes sense. But the other cool thing is you also see semantic relations in the vertical direction here, in that Spain and Portugal are closer together because they're more related as countries than, say, Spain or China. So there's a tremendous amount of structure and information in these high-dimensional spaces. Okay, so in summary, I hope I've shown you that this approach of building really deep networks that can build these high-level representations from fairly raw forms of data is pretty promising in a bunch of different domains: vision, speech, natural language processing, kinds of things. And being able to automatically construct good models from raw data is really valuable, because we're not hand engineering a bunch of features that enable us to recognize a cheetah. The model itself is learning what are the right sets of abstractions in order for me to be able to do a good job of discriminating a cheetah from, you know, a garbage truck and a lion and all the other kinds of things you might want to recognize. Okay, so part one, the brief part of the first part of the talk. You can build low latency services out of variable latency parts. And part two, being able to scale deep learning to very large models and very large data sets seems to be giving promising results. And there's lots of interesting work. I'm not a machine learning person, I'm more of a systems person, but I thought this seemed kind of interesting. And there's lots of interesting work at this intersection of systems and machine learning. You know, when we're scaling our training systems and looking for algorithms to train these models that are tolerant of asynchrony, you know, there's a lot of give and take in what kinds of things we can do on the machine learning side, which kinds of things will actually do a really good job of allowing us to scale on the systems side. And we need to sort of have a whole bunch of people with different kinds of expertise working together to actually train and build these large systems. There you go. Okay, I'll point out this is joint work with many collaborators, too many to even list on a single slide. But many of them are listed on papers that we've co-authored. And I'll take any questions. So the question is, what is the training data for these high-dimensional embedding vectors? In that particular case, it was just text from news articles. Yeah, the essence of the skipgram model is you're actually using a single word to try to predict nearby words. And you try to predict the succeeding or preceding word more often than you try to predict one that's two away, but you do it out to some window of maybe 10 or 15 words. So that's essentially the training algorithm, is predict nearby words with nearer ones being more of your training sample. The question is, what about parts of speech? The modeling does not include parts of speech, but if you wanted to train a part of speech labeler, the embedding space would be an excellent place to start, because if you notice the stab example, all the nearest things were verbs, essentially. And the fruit example, all the nearest things were nouns. And so in these embedding spaces, the parts of speech are widely separated. And it would be pretty easy to train a model that, you know, given a word, tells you what the part of speech is if you had a little bit of label to it. The question is, did we try the speech recognition example for multilingual speech recognition with non-Latin, non-European languages? And we have not. I believe the speech team has. I don't know the results. The results we brought up in the paper were all kind of the 10 European languages. The question is, are we pushing this down to hardware? And I'm not. The question is, are we looking into combining analog and digital data? I mean, when we get the data into our networks, it's all digital, you know, floating point values. So it might be interesting, but I think
performance. Yeah,
we haven't really explored that. So the question is, if you just wanted to build a cow or not cow classifier as opposed to a general 1,000 class object labeler, would you be able to get away with a smaller model? And the answer is yes. Yeah. The question is, could we use cascaded models that make simpler decisions and use a whole sequence of them to make the same ultimate decision versus just training the whole thing? We have experimented with that a little bit, and we found that they're kind of finicky to get right, and if you're able to, it's better just to train the whole darn thing. So the question is, which of the systems use backpropagation? I mean, backpropagation is essentially training via stochastic gradient descent. So all the systems that I described that were neural nets use backpropagation. The question is, do we not do the unsupervised paths? We initially did a lot of work on unsupervised learning, but we've come to the realization that there's a fair number of labeled data sets in the world that are easier to get systems to. If you have a big labeled data set and it is labeled for the task you care about, you're almost always better just training directly on that if you have enough data. If you don't have enough data, that's when you consider unsupervised training. The question is, we don't have labeled data for the intermediate layers in the network, but that's what those features learn to discover on their own. The lowest layer features in an image model are essentially learning edge detectors at different orientations, and then as you go up one level, it's learning kind of slightly more complicated versions where it combines edges together to make corners or kind of arcs or things like that. And as you go higher and higher, you're building up more and more complex features in these models. So as you get up to like 5 layers up, you're getting like ears and noses and parts.
All during backpropagation.
All during backpropagation, just directly from the top. Could I speculate on larger and larger systems?
Well, I think you get more and more layers or larger features. You see bigger, higher level representations.
Yeah, well, I think you'd like to be able to train bigger and bigger networks because you do better on a bunch of tasks, and that would be good. I think that's what I will speculate, is that bigger and bigger data sets will be better.
Maybe he's asking how long it will become better than people.
We have seen some limited tasks where we actually have enough labeled data and we're actually better than people in some certain limited domains. Humans are fast, well, not the speculation. Humans are very fast at identifying and processing visual data because they don't completely capture everything in the scene, right? If I just look at something quickly, I can't remember every scratch on that wall. But I can get the general high-level picture that there's a wall there and there's some people sitting. That's what these models are doing. These high-level features are capturing the most salient high-level features in that image. They're not capturing at the bottom, except very temporarily, in order to pass on to the next level, what are the lowest level features in these. I mean, I think the main thrust of your point, and it is a good one, is that we essentially need to be able to have very large models, only parts of which are active on a given example. That's the only way, that's why the brain is so energy efficient, essentially, is that when I look at a person, I'm not activating huge portions of my visual pathway that are not related to processing people-like things. How do these systems work in the image models, especially for translation, rotation, and scaling? So the answer is they work pretty well, especially the convolutional models. The convolutional models deal almost perfectly with translation, because if you think about it, I'm applying the same weights, whether it's here or here, and I'm going to get just a shift in the activations in my neurons of that layer and the layers above based on where that thing appears. So that's one nice property of convolutional models. For rotations, in general, you can do some regularization and things that make the models tolerant to slight rotations, but the current models are not very good if you completely rotate it. Those neurons are not necessarily going to recognize things, but other neurons, if you have training data, will fire when it's in a very different orientation. And so they can be fairly tolerant, but it's not as though individual neurons are kind of tolerant to a certain degree, and then you have to rely on other pieces of the model taking over. The observation is the more training data you have for faces in the right orientation, the harder it is to look at one that's not in the right orientation, and you take longer to process the time. Yes, that's true of these models. Like if you've never seen an upside down face, it's not going to do very well. But if you've seen a few, then it'll do okay. If you see a lot, it'll do great. The question is, these algorithms are highly parallelizable. It turns out that's not entirely true because stochastic gradient descent is inherently kind of a sequential algorithm. Within the model, there's a lot of parallelism, but ideally, you'd like to apply the gradients from one little batch of images completely before you start processing the next little batch. And so that kind of introduces a lot of sequentialness into the computation that you'd rather avoid. Now, we've been able to kind of skirt around this with some level of asynchrony, kind of order 10 to 100 model replicas all beating on the same set of parameters, and that sort of seems to work. But I wish the algorithms were more parallelizable than they are. But within a single model, there's plenty of parallel computation to do. And you can use GPUs, you can use CPUs. We have a lot of CPUs, so we tend to use those. The question is this being applied to financial data? Not by me, but I'm sure if you talk to financial people in other companies, I'm sure they would be applying these sorts of approaches to financial data. What kinds work best, or what kinds do we use?
Well, which
Both. Yeah, which is the best?
We use C++ because we have a lot of infrastructure code built in that. It's okay. It's efficient.
Yeah.
That's what you care about when training big models, because you can train bigger models. It's efficient. The question is, if you change the order in which you look at examples, does that change your model? Generally, it will change. The model won't be completely the same, but generally it'll converge to roughly the same level of performance for the actual output, which is what you really care about. But if you write training with one sequence of examples, they give you a very different local minimum than training with a different sequence of examples. So the question is, can we combine the knowledge graph with the image model? Yeah, we actually can, because we know a mapping from the object labels to knowledge graph nodes, and then we know, given an image, what label that fires.
Yeah, I heard in a previous talk from the guy that's from machine learning guy from UC British Columbia that's at Google now. He said you were using Freebase articles to help you on YouTube. Did you guys use Freebase?
So the knowledge graph has Freebase entries in it, plus a bunch of other ones. So in some sense, anything we do with the knowledge graph is in some sense using Freebase. Okay, thank you very much.